this is actually, you wouldn't know this, my second time through this video. I made too many mistakes. I had to go back and fix them all. But anyway, good to see you, or good to imagine you watching this video. So let's get into it. Enthalpies, something like the heats and energy flows in a reaction. And there's a way to calculate the energy change during a reaction. And there's tabulated values for these things called standard heats of formation or standard enthalpies of formation. The little circle up there, that means standard. The F means the formation. The H means enthalpy, and the triangle means the change in. So usually we're talking about 1 atmosphere of pressure and 25 degrees Celsius. If I was going to form a compound from its particular elements, then I might ask the question, how much heat is associated with that? Because compounds are more stable usually than the elements they come from, although not always. These delta H values, standard heat enthalpies of reaction, are almost always negative, almost always exothermic. So if I were going to make some copper oxide from copper and oxygen, I would release 156 kilojoules per mole. So if I form 1 mole of this from 1 mole of this and half a mole of O2 gas, gives off heat. If I were to take 1 mole of carbon, that's copper, that's carbon. 1 mole of carbon, 2 moles of chlorine gas to form carbon tetrachloride liquid, I am told, I looked it up, they measured it, gives off negative 134, or gives off 134 exothermic, negative means exothermic, kilojoules of heat. And the list goes on and on and on. It's just crazy. Some of these reactions aren't really doable in the laboratory. You'd have to have a plant to do it in several steps. So like making this alcohol, that's going to be a several step process. Or I take 2 moles of carbon, 3 moles of hydrogen gas, half a mole of O2 gas to create 1 mole of ethanol liquid. And the heat for that, negative 278, so I'm told. And again, we never balance chemical equations with fractions, but these thermochemists will often say, I just want 1 mole of this, so let me take half a mole of that. Or I could take 2 of these, 1 of these, 6 of these, and 4 of those to release twice as much heat. So the amount matters. Sometimes they're endothermic, like if this chemical, HCN, hydrogen cyanide gas, nasty gas, is created from hydrogen and carbon and nitrogen, then this has more energy than the the reactants separate. So it's endothermic. You have to pump energy into these reactants to make them do this. Yeah, and often it's not just a single step like I'm writing it here, but we're just speaking hypothetically, theoretically. These are where the numbers come from. They're measurable. Or we can write it as a as a product or a reactant. So if it's endothermic, my number goes on the left, or sometimes I'll just write the word energy or heat over here. And if it's exothermic, I'll write the number of kilojoules on the right. Sometimes we'll just write heat or energy on the right. So if it's on the right, exothermic, endo going into, exo exiting the reaction. Also, the phase is very important. Don't forget about solid, liquid, gas, aqueous. So if I'm looking up H3PO4, for example, sorry, my MOL got cut off, MOL per mole. I'm looking up phosphoric acid solid, phosphoric acid liquid. There's no difference in any of these equations except for the solid, liquid, or aqueous. And in the phosphoric acid example, the numbers change slightly. In other examples, there's a huge difference between solid or liquid and or gas and or aqueous. So you make sure you pay attention to the phase. Let's see here. Shrink down a little bit. What else am I trying to say here? More examples. Again, this is a summary of making a sugar from carbon, hydrogen, and oxygen. Humans couldn't do this in one simple step. Even plants can't do it in one simple step, but there's a series of processes to go to synthesize overall 6 carbons and 6 hydrogen molecules and 3 oxygen molecules. And of course the plant doesn't necessarily use hydrogen gas, but I'm just saying this heat is associated with that reaction. Exothermic, exothermic. They could be called something other than heats of formation. For example, if I'm breaking apart the chlorine gas into chlorine atoms, then I could say this is the dissociation energy for chlorine. Although if you looked up the dissociation energy for chlorine gas, it would say 1 mole of chlorine gas would be endothermic to the tune of 243.4 kilojoules for 1 mole. That's because here in my thermochemical equation, I wrote a half a mole of chlorine gas breaks down to give 1 mole of chlorine atoms. Crazy. Again, exothermic could be written in the equation, and this energy level diagram goes with it. Very important. You should study it, sort of, or the shape of it. Most reactions being exothermic will start off with a reactance high and the products low, so I give off an amount of heat if I go from here to here. It'll be very, very usually exothermic. And also there's an activation energy, so I may have to get up over this bump. But if I can get my reactance up over this bump, then I can sort of fall down the energy hill to release energy and form the products. Similarly, yet oppositely, for endothermic, so here's an endothermic at 11.3 kilojoules. I could write it on the left or write it separately as a positive term for my delta H of formation. And endothermic, everything's flipped backwards. So I see my reactants down low, my products up high, and I have to push them up this huge activation barrier with a whole bunch of energy, even a little more than 11.3, a little bit more than 11.3. I'm not sure how much for this reaction. But as soon as I stop adding that energy, then this thing would stop going up the hill, and so my products stop being formed. But as long as I'm adding the activation energy or energy to overcome the activation barrier under the right circumstances and conditions, then I can do it. All right. Also, the standard enthalpies of formation for pure elements, always 0. Got to remember that. Got to know that. So hydrogen gas, oxygen gas, fluorine gas, chlorine, iodine solid, carbon solid, silicon solid, bromine liquid, iron solid, you name it. Choose an element. Choose an element in its normal condition, normal standard state, and the delta H of formations are 0. So why do we care? There's a very useful equation. It goes like this. Products minus reactants. If I knew the enthalpies of formations for the products and the enthalpies of formations for the reactants, I just subtract them. Also important, of course, are the coefficients in front. So for any particular reaction like this, if I have numbers m, n, x, y, could even be fractions in the thermochemical setting, I just take products minus reactants. When I look these numbers up in the back of the book or in tables online, usually they vary a little bit from table to table, but are pretty close. Yeah, so what does that look like? It looks like this. I snipped this from the ebook of our text. Let's see, looking at just a couple of them. Bromine. So also, we're given delta G and S. We don't know what those numbers are yet. Or some of you may have talked about them, but we have not. So we're talking about just the enthalpies of formation. So for pure bromine liquid, 0. But if I want to form bromine gas from bromine liquid, it takes some energy. Endothermic, actually. But you'll notice many of them negative. Exothermic. So if I was making carbon monoxide from carbon and oxygen, it's carbon and O2 gas, or carbon dioxide, even more exothermic. So these are the numbers I'm looking up. I'm looking up these delta H numbers right there. All right, let's see. So let's practice that at least once or twice or thrice. Here's a reaction, a combustion of propane. 5 moles of oxygen, 1 mole of propane. I could also call it a heat of combustion. But I'll take products minus reactants. The products are 3 moles of carbon dioxide, 4 moles of water, 3 moles of carbon dioxide, 4 moles of water, 1 mole of propane, 5 moles of oxygen. Those are the reactants. I just sort them out, try not to make a mistake. Oxygen's a pure element in standard state, so 0 for its number. And lo and behold, exothermic. But I'm not surprised because combustions and burning things are always exothermic anyway. Let's try another one. This one, also endothermic. This one also exothermic. So 1 mole of this, N2O4, 4 moles of hydrogen gas, 1 mole of nitrogen gas produced, 4 moles of water vapor produced. So products, 0 for this one, 4 moles of water, minus reactants, 0 for this one, 1 mole of this one. And lo and behold, exothermic. Not surprising. Another slight twist on the theme would be to say, what if they gave you the heat for the overall reaction? So I have the heat for this reaction, and I also have the heat of formation for this, but for some silly reason I can't find the heat of formation, or I'm wondering, according to this data anyway, what's the standard heat of formation for this SO2? So as usual, I just go products minus reactants, but if I'm given this, the overall delta H for the reaction, positive 89.5, I fill that in there. The product, there's only one product, it's negative 204 was the heat of formation for it. And the O2 gas is a pure element, doesn't matter if there's a half in front, half times 0 is still 0. This is the unknown, solve for the unknown. And of course, exothermic, most compounds have an exothermic or a negative delta H at formation. So that's just algebra, but a trick, a twist. Also important, we can use these heat numbers for a particular reaction equation to say, well, if I don't use a full portion, a full recipe, a full amount, according to the stoichiometry, the balanced equation. So this says 4 moles of this, 5 moles of this, give 4 moles of this, and 6 moles of this. But what if I don't want to create that much? What if I only want to use 155 grams of ammonia? Well, let me change 155 grams of ammonia to moles of ammonia. 17, or 155 divided by 17, 9-ish moles of ammonia. Then here's the real kicker. You see this conversion, this energy term, this kilojoules, that's written separately from the equation, but really it could go with this, or it could go with this, or it could go with this, or it could go with this. So if my question is about ammonia, I know that 4 moles of ammonia react in this fashion to give negative 906 kilojoules. So I wrote 4 moles of ammonia give negative 906 kilojoules. The moles of ammonia cancel. I go to do the math, 906 times 9.12 divided by 4, and energy released. Oh my goodness, yeah, quite a bit. What is that? 9 moles. Ah, that's a bigger recipe, isn't it? So 9 moles is bigger than 4 moles. So 9 is more than twice this number, so this is more than twice this number. This is more than twice of this number. Ay, chihuahua. All right, we could try that again. How many grams of water would be created in this reaction if only 500 kilojoules were released? Similar conversion factor. I can relate the kilojoule number given after the equation to the moles of water in the balanced equation as a conversion factor. Then also, lastly, I converted moles of water to grams of water, which this step shouldn't be too mysterious, but this is totally new and interesting, and the cancellation works like that. 59.6 grams of water. All right, do I have time for another? I might. Excuse me, one more slide. Excuse me again. What is this? Butane? I think it's methylpropane. Yep. Butane burns in oxygen. 4 moles of carbon dioxide, 5 moles of water. If you want to get rid of that fraction, just take everything times 2. Take it times 2, take it times 2, take it times 2, take it times 2, take it times 2. What mass of carbon dioxide is produced when 1,500 kilojoules of energy is released? Well, 1,500 kilojoules, isn't that more? No, it's less. It's what? Excuse me. It's less than this number, right? Yeah, so I'm doing less than a full recipe, less than 1 mole, less than this, less than that, less than that. But how much am I talking about? Well, let me start with that 1,500 kilojoules. That was the number, the number I was thrown. And say it's exothermic, but so too is the reaction overall at negative 2658 kilojoules. And that's for 4 moles of carbon. Oh, no. Oh, just a little typo. No. Dang, I screwed that up again. Hang on a second. It's like the 17th mistake I made on this video. Be right back. All right, sorry about that. So I'm talking carbon dioxide. 4 moles of carbon dioxide associated with the release of 2658 kilojoules of energy. So there we go. 4 moles of carbon dioxide, this much, this number of kilojoules of energy. This is released, so the kilojoules cancel. Moles of carbon dioxide change to grams of carbon dioxide, and voila, lo and behold, 99.3 grams of carbon dioxide. Lord, I got to change that. That's a 2 right there, carbon dioxide, before I PDF this. All right, what else? Oh, in passing, here's one for you if you want to try it. How much energy is released during the consumption of 100 grams of oxygen? So up here, if I had 100 grams of oxygen, how would that relate to moles of oxygen? And how would this and this give you your answer in terms of kilojoules? How much energy? Thanks, guys. I'll see you in class.